Good morning, dear students. I am Dr. Srinivas Bhattani, Professor of Chemistry in Sri Academy, Hyderabad. In the last video, we have discussed resonance effect, that is belongs to displacement of electrons. That is mainly fundamental concepts. And before that video, inductive effect also we have discussed. So now, today we are going to discuss about the electromagnetic effect and hyperconjugation. Hyperconjugation is very important for that IIT students, and how to write the mechanism, how to displacement of the electrons, mainly in fundamental concept. That is more important for writing of mechanisms. Okay, first we have to discuss about electromagnetic effect. Just we have to do, I will tell you the definition of the electromagnetic effect. So then we have to discuss the third one is the electromagnetic effect. Electromagnetic effect. The first one is the inductive effect. Second displacement of electron is the resonance effect or mesomerific effect, and third one is the electromagnetic effect, and fourth one is the hyperconjugation. So these are very important for writing mechanisms. So electromagnetic effect, what is meant by electromagnetic effect? It is purely temporary effect, and play instantaneously at the demand of the attacking reagent. So what happened? Mean the complete transfer of the shared pair of electrons, multiple carbon bond to one of the atoms in presence of reagent is called electromagnetic effect. If you have to know just example, then we can understand. What is that example? The addition of acid to the alkenes, the best example. So in the presence of reagent, addition of acid, either hydrochloric acid or sulfuric acid to alkene. For example, this is the propene. We have to take the propene, CH, double bond CH2. This is called the propene, alkene. So when alkene in the presence of reagent, that is H plus, either HCl or sulfuric acid or any acid, that is protonation takes place, that is H plus. When what happened here, we can write from this side. H plus to form. So what happened here? That is it's a temporary effect. This pi bond come to this side, and it will get the CH plus ions. CH3, CH plus and CH3. The formation of this, the carbocation. This is the temporary effect. Okay, this is about the electromagnetic effect. What is the electromagnetic effect? The complete transfer of shared pair of pi electron. This is the shared pair of pi electrons of multiple bond. Multiple mean double bond or triple bond, whatever the bond is there, to one of the carbon atom. Mean this side. This is the one of the atom. In the presence of reagent, that is the hydrochloric acid or H plus ion reagent. Okay, so this is about the electromagnetic effect. Okay, now that is a very important. The last topic is what? Hyperconjugation. Okay, that is a very important topic. Is what? Hyperconjugation. hyperconjugation. And other names also there. What are the other names? No bond resonance effect. No bond resonance effect. Or we can say no bond resonance. No bond resonance. Or this was proposed by the Baker and Nathan scientists. So we can say Baker-Nathan effect. Baker-Nathan effect. So these are the names. Baker-Nathan effect. So what are the conditions of the hyperconjugation? Conditions are very, very important for the hyperconjugation. Please listen carefully. So what is that? The conditions are most important in this topic. So that is that it must be alpha carbon hydrogen group adjacent to sp2 hybridization. What is that? Alpha CH. Alpha CH must be where adjacent to sp2 hybridization. Adjacent to sp2 hybrid carbon. sp2 C double bond C. That should be containing the alpha CH. Alpha CH. That is the condition. So if it is not there, there is no hyperconjugation. If it should be present. So what happened? If it is there, delocalization takes place. The delocalization of the delocalization of sigma electrons of CH bond adjacent to pi bond. The pi bond is present on the sp2 carbon atom, and this is the alpha CH bond is the sigma bond. That is what happened, that sigma electrons of carbon hydrogen bond adjacent to pi bond is called the hyperconjugation. Understand? Once again, please listen carefully. The delocalization of alpha electrons of carbon hydrogen, the CH, the delocalization adjacent to sp2, that is double bond, mean pi electrons. We can say simply pi bond is called the hyperconjugation. Okay? So example, we can take the example. What are the examples are there? Alkenes, alkyl carbocations, alkyl free radicals, nitro compounds with alpha hydrogens. All these are the examples. Okay, let's look the one example we can understand very easily. For example, we can say alkene. The propene, we can take the propene. For example, propene. This is the propene. Hydrogen. Okay, hydrogen. Propene, hydrogen. This is called the propene. Okay, so that pi bond is there. This is the sp2 hybrid. Mean pi bond. We can say this is called the pi bond, or we can pi bond. This is the pi bond. So which one is the sigma bond? This is called the sigma bond. So sigma CH, alpha carbon. Okay, so pi bond is there, sigma bond is there. Then this is the rule, it must be present. So one pi bond is there, that is the sp2 carbon atom. Okay, and sigma bond is there. Now hyperconjugation takes place. How? So this pi bond come to this side. Okay, so otherwise we can say this is the okay, and the sigma bond come to this side. The sigma bond comes. What happened now? So here H And this one. So here the bond came in 2 electrons. One bond is equal to 2 electrons. So the 2 electrons are here. That is the minus charge. Minus charge. And H plus, the H plus sigma bond electron. Here simply H plus. Okay, that H plus ions. Okay, this is the hyperconjugation effect. CH2 double bond C negative means CH2. So this will happen. So this is called the hyperconjugation. So please, for competitive exam, the applications are very important. So the applications mean that will ask in applications. First application is the what? Stability of alkenes. So the stability of alkenes of hyperconjugation. All the alkenes are there. What happened? Increasing order of stability of alkenes with increase in the number of methyl groups on the double bond. Okay. For example, I will write here. Please note down everything. For example, increasing order. We have to write the increasing order. CH double bond CH. Here, what happened? CH double bond CH2. Sorry, CH. We can write CH2 double bond CH2. Okay, there is no methyl group. Now, one methyl group added. CH3. This is the order. Okay, now is less than 2 methyl groups. Increasing order of the stability. Now say like this order. Increasing order of the stability of alkene with increase the methyl group on the double bond. See here the 4 methyl group, highest groups are there. So it is a higher stability is there. Mean this compound is having higher stability due to the hyperconjugation effect. This one is the alkene, ethene is the less stability, less. Here, this one is the more stability because the methyl group is increased. Number of methyl groups are increased. This is the application. You have to remember that in the competition exam they will ask you. So, mean the number of groups are increased. The stability is increased. Less the number of, so less stability. More the number of, more stability. Okay, this is one application. And second application, please note down it. And second application is one butene and comparison between the one butene and two butene. So among these two, which one is having a more stability and why? One butene, we can say one butene, that is a CH3 double bond CH2, one butene. Okay, so CH3, CH2, we can write like this. CH 1, 2, 3. You can write like this. This is a one butene. So 1, 2, 3. Okay. We can take the butene one example, that is CH3, CH2. Okay. So this is the one butene, because here 1, 2, 3, 4. So one carbon containing the double bond, that is one butene. So in the case of 2 butene, so that is CH3. So this is the 2 butene. 1, 2, 3, 4. So this is the carbon containing the double bond. That is the number 2 carbon having the double bond. So we can say 2 butene. So this is 2 butene. This is 1 butene. 1 butene and 2 butene. These two compounds mean 2 butene and 1 butene. Which one is more stable? 2 butene is more stable than the 1 butene. Why? 2 butene. So it is a more stable. More stable. Because the reason 2 butene have more number of hydrogens. See this one. This carbon containing the methyl group means 3 hydrogens and 3. Total 6 hydrogens. Whereas this one, this CH group, only 2 hydrogens are there. So there is no hydrogen, third string carbon atoms. Only 2 hydrogens. So that is the main reason 1 butene is having a lesser stability than the 2 butene. Because the reason 2 butene is having the more number of hydrogens. This is the second applications. In the case of propane, if you are taking the propane and butene, so this is the butene, for example, this is the butene, compared to the propane. So we have to compare the propane and butene. For example, CH3 double bond CH. A, this is B, okay, C compound. Now, compared to between the A and B, butene is the more stable. And compared to A and C. So, among these two, which one is more stable? A and C. A and C mean propane and butene. So among these two, which one is the more stable? Among these two, mean the 1 butene and propane. The propane has more hydrogen atoms than butene. More hydrogens. Where the propane has more hydrogens, because here the only 2 hydrogens are there, and here 3 hydrogens are there. 3 hydrogens are there. So due to this 3 hydrogens, the number of hydrogens are more compared to here. So this one is a more stable than this one. And among all these things, the B is more stable than the C. C is more stable than the A, because the number of hydrogens are more. So this is about the stability of compounds depend upon the hyperconjugation. Okay, if we can take the stability of the carbocations, increasing order of the stability of carbocation, increasing order. Carbocations mean CH3, CH2 plus, CH3 plus, like that, increasing the carbocation. Mean methyl carbocation is less than the primary carbocation, is less than the secondary carbocation, is less than the tertiary carbocation. So mean the carbocations, the stability, another applications of hyperconjugation Another applications of hyperconjugation, that mean the increasing order of the stability carbocations, mean methyl carbocation, methyl carbocations, carbocation, methyl carbocation is less than the primary carbocations. Primary carbocation is less than the primary, then is less than the tertiary carbocations, and is less than the tertiary carbocations. First of all, methyl carbocation is less than the primary carbocation, is less than the secondary. This is one secondary is less than the tertiary carbocations. Methyl carbocation is less than the primary carbocation, is less than the secondary carbocation, is less than the tertiary carbocations. Mean CH3, CH2 plus in these two cations, hyperconjugation is not possible. In CH3 plus main carbocations, the ethyl carbocation is more stable than the methyl carbocation. Because among these two, for example, CH3, CH2 plus and CH3 plus, so in this ethyl carbocation is more stable. So this is the more stable than this one. Mean it's a greater stability, more stable than the methyl carbocation. Actually, in this two cations, hyperconjugation is not possible. But among these two, this is the most stable. Okay, that is about the stability of the carbocations in hyperconjugation. Finally, the stability of the free radicals. Stability of this free radical also. The methyl carbocations is less than the primary carbocation, is less than the secondary carbocation, is less than the tertiary carbocation. Same order. Okay, same order. So reactivity and orientation of electrophilic substitution on benzene ring. For example, you have to take the toluene, the methyl group. The toluene means the present here that benzene ring containing that CH3. So this is the toluene. Here the methyl group is there. That means in the methyl group, the release of electrons towards the benzene ring, the partial due to the inductive effect, mainly hyperconjugation effect. The reactivity of the ring towards the electrophilic substitution increases, and the substitution is directed to ortho and para positions. How it is possible? So let's look. This is the last and final. So in the toluene, hyperconjugation effect is, for example, here. So this is the toluene. So what happened here? That this bond come to the side and this will come to the side. And what happened here? This one ortho position and this will happen. So and then again, so this will come to the side, okay, and the para. This is the ortho and para. So then this will happen. And this will happen. Then again like this. Will come in. Okay, this will happen. So this is the main especially reactivity and orientation of electrophilic substitution on benzene ring. If any group is like there. Okay, so one more, the final reverse hyperconjugation occurs in alpha. This is very important. Reverse hyperconjugation occurs in alpha alloalkanes. For example, propene containing the chloride group. For example, that is the reverse hyperconjugation. This is the best, very very important. The chlorine group containing the CH2 propene, C double bond CH2. So this is CH. So this is very very important. Here reverse means reverse side. That electronegativity atom is present. So this will come among this one. So this will become salt. This is the reverse hyperconjugation. So this is a reverse hyperconjugation. We can say reverse hyperconjugation. Okay, that is CH2, CH, CH2, CH plus, because this one is the plus. And Cl minus. This will happen. Okay, this is called the reverse hyperconjugations. This is the alpha haloalkane. This is the alpha haloalkane. Alpha position. Okay, this is the functional group, alkenes, alpha position, alpha haloalkanes. That is the reverse hyperconjugation occurs. Okay, so thank you very much. Please don't forget about the subscription. Okay, thank you.